By now you're probably familiar with the ballistic pendulum problem, a classic physics problem, either from your studies and previous classwork or from a lab activity. Well, we're going to take a little closer look at this problem using a more realistic ballistic pendulum. For our previous examples, we treated the pendulum as a simple pendulum. A simple pendulum means that the string or the rod is massless and all the mass is in the end, at the end of the string or rod. When the collision took place, we could use linear momentum to get through that collision because all the mass was in the point at the end of the rod, at the end of the string. But really, oftentimes we have a pendulum that is not a simple pendulum. We call that a physical pendulum, where the mass is spread out. There is some mass along the rod in addition to at the bottom, or in this case, I'm not going to have any mass at the bottom, just the rod. So here I have my pendulum, and it's free to rotate about an axis through the end, but my mass is spread uniformly along the rod. When the clay ball hits it, it's going to stick to it, and the two objects will rotate up together, as you see in my drawing. So if we were given the initial speed of the clay ball, the mass of the clay ball, the length of our rod, the mass of the rod, and we're going to treat the clay ball as being very small compared to the length of the rod. So we can treat the clay ball as a point mass. We want to find the final angle. When this thing rotates up and just comes to rest momentarily, what angle does the rod make with the vertical? So we're going to try to find theta. Let's think about this problem. What lenses can we use to get through this problem? Can we go from the beginning to the end using energy? No, we cannot, because there's an inelastic collision in the middle. We know for sure our mechanical energy is not going to be the same before and after this collision because these objects stick together. Can we go from the beginning to the end using linear momentum? No, we can't. This rod is attached to the earth. And so the ball starts out with lots of linear momentum, then it hits the rod and tries to keep going, but the rod is attached to the earth at the axis, and it can't move in that direction. Can we go from the beginning to the end using angular momentum? No, because the earth gets in the way and pulls on it. There's certain angular momentum before the collision, there's a certain angular momentum after the collision, but then as the rod starts to rotate up, external torque acts on the system and slows it down. Gravity acts on the system and slows it down. What do we do in a case like this? We break it up into multiple problems. Where do we always split our problem? The split second before the collision and the split second after the collision. So I'm going to draw a timeline. I actually already drew the timeline for you. I'm going to call this time 1, this time 2, and this time 3. Time 1 is just before the collision. Time 2 is just after the collision. And time 3 is later. Sometimes you have to do something earlier, sometimes later, but you always split the problem the split second before the collision and the split second after the collision. Now I can go through the collision using angular momentum. Because this is a solid rod with mass distributed along its length, I cannot use linear momentum to get through this collision. But I can use angular momentum if I pick my time interval short enough that I say gravity really doesn't have a chance to act on this rod yet because it doesn't swing up. The clay ball hits the rod starts to move, but gravity really hasn't had a chance to affect it yet. And I'm going to just take a look at that split second before and after the collision, and I can use angular momentum. I can approximate that as being a system with no net torque on it for that tiny, tiny time interval, and I can use angular momentum. But I know that if I allow that rod to continue to swing up, I can't use that assumption anymore. Gravity is acting on it, changing its angular momentum. So after that split second after the collision, I can't use this anymore. But what can I do? I can use energy to see how high up it's going to swing once I know the speed just after the collision. So we're going to split this problem up into two problems. First, we're going to use angular momentum to get through the collision because momentum is our go-to lens when we have collisions. In this case, we'll use angular momentum because of the object rotating. And then we'll use energy, rotational energy. The angular momentum at time 1 has to equal the angular momentum at time 2. This is a vector equation. I need to define a positive direction. I'm going to call counterclockwise, or to be more precise, out of the page, as my positive direction. Because everything is moving in that direction, I'll just call that the positive direction. The clay ball is coming along, and if it strikes this rod, what's the rod going to do? The rod's going to rotate in the counterclockwise direction, or with an omega that points out of the page using our right hand rule. And at the end, the rod is rotating counterclockwise, or with an omega out of the page. So all of our angular momentum is positive. At time 1, I've got a clay ball and I've got a rod. And at time 2, they're stuck together. So I'll just call that L clay plus rod. The rod is not rotating, it's not moving, it's not doing anything initially. Its angular momentum is 0. But the clay ball is moving. It's moving in a straight line. So how do we get the angular momentum of an object moving in a straight line? It's the mass of the object times its velocity times the perpendicular distance to the axis of rotation. So let's take a look at that. If we draw a line for its momentum, its velocity, we want to find the perpendicular distance to the axis of rotation. That's just the length of the rod. If the clay ball strikes the rod right at the base of the rod, d perpendicular is just the length of the rod. I'll try to remember to use lowercase l's for the length of the rod because I use capital L for the angular momentum. I don't want to get you confused with two symbols that are the same but have different meanings. So I'll try to remember to use lowercase l for the length of the rod and capital L for angular momentum. So we've got an object moving in a straight line that has angular momentum. We have an object sitting there at rest that does not have any angular momentum. That's our total angular momentum at time 1. At time 2, we have an object that's rotating. How do we find angular momentum for an object that's rotating? I omega. And this is the total rotational inertia of the rod plus the clay ball stuck to the bottom of it. So the rod is just rotating about its endpoint. Its rotational inertia is 1/3 m rod L squared. And the clay ball is just a point mass. We said we're going to treat it like a point mass because it's small. It's the mass of the clay times the distance to the axis of rotation squared. That's L squared. So this is I for the clay. This is I for the rod. And we're multiplying by omega at time 2. So if we're given all this information, we now know the angular speed, omega 2, of the rod plus clay ball the split second after the collision. So we can use energy to see how high the rod swings up. The mechanical energy at time 2 is going to be the same as the mechanical energy at time 3 because there's no friction in our system and we're including the Earth in our system, so there's no external work being done. Initially, things are moving, and at the end, we just have gravitational potential energy. So the kinetic energy at time 2 is 1/2 I omega squared. I we already found right here. Omega 2 we already found right here. So we can plug those in. We know the kinetic energy at time 2. What's the gravitational potential energy at time 3? Well, we can either find the center of mass of the system, or we can just treat the two individually. We can find the gravitational potential energy of the rod at time 3 and add that to the gravitational potential energy of the clay at time 3. So let's take a look at that. The clay starts out at the very end of the rod, and it ends up here. We want to know the height that it goes up. I'll call that HC. So if I look at my equation, I need to figure out the height that the center of mass of the rod rises and the height that the center of the clay rises. HR and HC. So let's take a look at the clay. First, we're trying to find HC. Well, we know this distance here, I'll use blue. This distance right here is the length of our rod, L. And this distance in here, I'll use red, is going to be L cosine theta. If we look at this right triangle here, the hypotenuse is the length of the rod. So the adjacent side is the hypotenuse times cosine theta, L cosine theta. So H sub C is just this gap right here. L minus L cosine theta. If you go through that same thought process for the rod has a center of mass here at L over 2. And that center of mass swings up to here, and the distance that it rises, H rod, we can find using the same thought process. Only instead of L, it's going to be L over 2. It's the same exact process. So we know the left side of this equation. The right side of the equation, we know everything except for theta. And we can solve for theta.